So now we're going to analyze the gain for the other two system responses. Vc, the voltage drop across the capacitor, or VL, the voltage drop across the inductor. So what we're interested in is the ratio of the amplitudes of our output and of our input. And we can understand that by looking at the magnitude of the complex gain. The complex gain are the two expressions that we have here. So big G of C is given by this expression, and big G of L is given by that following expression. We could analyze little g, which is the magnitude of this complex number, but we can actually gain a lot of information just by looking at the complex number itself. And that's what we're going to do. So let's look at some extreme cases for our driving frequency omega. So if we have omega going to 0, what happens to GC, the complex gain? So I can see that the numerator is not affected. It doesn't depend on omega, so the numerator stays the same. But the denominator grows as also a constant 1 over c. And when we look at the amplitude of this complex number, we see that we have 1 over c divided by 1 over c. So the magnitude of this is tending to 1. And the magnitude of this complex number is what we call little g, the gain. Now what happens at the other extreme? What happens as omega goes to infinity? As omega goes to infinity, the numerator is again dominated by 1 over c, but the denominator is now dominated by the term negative L over omega squared, negative L times omega squared. And now we need to think about the amplitude of the numerator and the amplitude and the magnitude of the denominator. And we see that the magnitude of the numerator is just 1 over c, a constant, whereas the magnitude of the denominator grows as omega squared. So this ratio is going to 0. So the ratio of the magnitudes, little g, is going to 0. So this is in the case of the capacitor, so we call that GC, so the gain for the capacitor. So it's 1 when omega goes to 0, and it's 0 as omega goes to infinity. Now let's look at the case of the voltage drop across the inductor, which is given by the complex gain GL. Again, the two behaviors. As omega goes to 0, the numerator goes to 0, but the denominator goes to the constant 1 over c. So we have that the ratio of the amplitudes, which is our gain GL, goes to 0. And finally, we look at what happens at omega goes to infinity. Again, the dominant term in the numerator is minus L omega squared, and the dominant term in the denominator is also minus L omega squared. As we compare the magnitude of these two complex numbers, that ratio tends to 1. So here we have the extreme limit behavior for the gain of the capacitor and the inductor. But now, what happens in the mid-range? So the analysis of the mid-range can be quite complicated. So we would have to solve the equation ddw of GC equal to 0 if we want to find a maximum for the gain of the capacitor GC. The algebra behind this can be quite tricky, but it can be shown that the gain obtains a maximum, so GC has max as long as R is small. So as long as the resistance of the system is small. We could do the same calculations for GL, but it can be shown that GL always has a maximum. So with this, we have enough information to make plots for both GC and GL. So let's recap. When omega is equal to 0, GC goes to 1. When omega goes to infinity, GC goes to 0. This means that the capacitor is allowing low frequencies to pass through, but it's not allowing high frequencies to pass through. So it's giving 0 gain for high frequencies. Whereas the inductor is doing the opposite. As omega goes to 0, the inductor has gain of 0, but when omega goes to infinity, the inductor, the voltage drop across the inductor has gain of 1. So let's make a plot with this information. Just for reference, I have the plot for the gain for the voltage drop across the resistor, which we found previously. So let's draw the other two gains now. So this is, again, omega, and this is G of C. And this is omega, and this is GL. So the gain for the capacitor, it goes to 1 when omega is equal to 0, and it goes to 0 as omega goes to infinity. Like I said, there were two cases that can happen. If R is small, there will be a peak. And I'll draw this curve in a different color to indicate R small. Now, the other case is if R is too large, then this peak disappears, and the function just smoothly decays to 0. So this is for R big. So these are the two possible scenarios for G of C. Now, let's look at the behavior for GL. So GL goes to 0 at low frequencies, and it tends to 1 at high frequencies. And this function GL always has a maximum for some finite value of omega. So we'll draw this as such. So let's look at a few applications from what we've just found out. So if we look at the graph of GC, we see that it allows low frequencies to pass through, while high frequencies are inhibited, so they tend to 0 at high frequencies. This means that if you want to build something like a speaker and you measure the voltage drop across the capacitor, then you would have low frequencies passing through, and that would be equivalent to a woofer speaker that has strong bass and low treble. The opposite is true for GL. If you pick the voltage drop across the inductor as your system response, you would not allow low frequencies to pass through, but you would allow high frequencies to pass through. And that would be something like a tweeter speaker, which has high treble and low bass. So high frequencies pass through. Right, so these are some applications for using an RLC circuit for building speakers. We can also build a very primitive AM radio using an RLC circuit, but in that case, measuring the voltage drop across the resistor as our system response. So if we look here, the gain GR obtains a maximum for a specific value of omega. So this means if I'm trying to pick a station, I would have best reception if the frequency of my input is near this resonant peak. But note that this peak is pretty wide. So this radio wouldn't be the best radio in the world. We would pick quite a large band of frequencies. So in order to make a better radio, and in order to make better electronics in general, you need to combine a lot of these circuits. And when you do that, you can amplify your response the way that you want. So these are just some basic applications from a single loop RLC circuit.